Yeah, the experiment 2, the Hess's laws due Thursday. Not just the graphs, but the graphs and calculations. Thursday is when it's due. The rough draft for the KCLO 3, I'd like to see this week. So far I've seen one today after class, but and then last week I saw a few. So get started with your rough draft. I'd like to see rough draft. Okay.
It can be written or as a type.
It doesn't have to be typed. It could be handwritten.
Just legible, right?
You don't turn it on. I'm just going to look at it and I'll give it right back to you. It's not something you'll hand in. It's not worth points, but I'd like to see something. The rough draft is. I'm sorry?
Is there a due date for the final draft?
The final draft, I'm gonna come up with a due date. After I see some rough drafts, then I'll get a better idea. I know yours is pretty much done, right? So you can turn it in early in that case. But the due date, I'll probably make the due date like in what? How much time do you think you'll need to do?
Should pressure us to the finals?
Isn't it like what?
I mean, exam 3.
Before exam 3 or after?
The week after exam 3. So.
All right, that's okay. We could do it
Like that
after.
Tuesday or Thursday right after the exam 3.
That works. Hopefully before then I can see a rough draft. And,
The written map.
No. I'm just saying
Monday?
no, I'd rather collect it on lab day, probably like a Tuesday or a Thursday. All right. Like the Thursday after the exam 3, that could work. Okay.
18.
I'll post it on Piazza then. So we did. We're still working on the sulfate. The sulfate will finish tomorrow. We're starting the new experiment, but it's easy to finish that. And the calculation for the sulfate, I'll talk about. Probably tomorrow I'll talk about the calculation. We're going to do a little bit of extra on the calculation, extra analysis. Are there any other questions? No? I'm going to try something new here. I'm going to do PowerPoint presentations. And I have a kind of a bias against PowerPoint because I like more informal presentations rather than formal. What made me want to try the PowerPoint?
Yeah, you have a bias against
Well, two things. One, I'm falling behind schedule, so PowerPoint helps me catch up usually. And two, then you have the PowerPoints. I posted all the PowerPoints on Piazza, and so you know what's coming up, and you can preview it, so you can get an idea. And then, and also PowerPoints are organized, which and so perhaps easier to follow. Okay. And so let's see if this helps. If it, you could let me know your comments. If you don't like PowerPoints or if you like them, that's, you can let me know. These are the PowerPoints from Petrucci, the book. I'm just using them as is, and I'm not going to change them. I'm just going to follow his presentation. But what I going to do is I'm going to add to it at times, or I'm skip certain things. basically we spent a lot of time talking. The reason we spend a lot of time talking about this internal energy and work and heat and all this other stuff is so we can better understand this one. This is what we want. Why do we want delta H? We want delta H because delta H is going to tell us the net, energy. It's like if you're going to go shopping, right? And you look at the price, but then you always have to think, well, how much do you have to pay in tax, right? Or, how much is it going to be out the door? You want the out the door price because, if you buy the item here in California versus if you buy it in Oregon there's no sales tax. Don't worry about that. And so we worry about the tax. So, we don't want the pre-tax price, we want the net price because this is how much energy we're either going to have to input or this is how much energy we're actually going to get. And so that's what delta H is. Delta H, if I do this reaction, do I have to care about the work? Was there work done in this reaction? Well, we're going from 3 moles of gas, 75 liters, to 2 moles of gas, 50 liters. So we lose 25 liters. So some work was done. For sure work is done. Work is done by the surroundings, but do we care? Not if we're using delta H. We don't care because most of the reactions that we do are under conditions of constant pressure or constant volume.
Pressure.
Constant pressure. And so as long as we do this under constant pressure, then I don't care. I lose 25 liters, it doesn't matter. It's going to happen at constant pressure. And I don't have to care. I don't have to worry about how much work that is because this is the after-tax price, right? Or after bonus in this case, price. So this is how much energy I'm going to net out of this. And so that makes it easier if I don't have to worry about that. The only problem is if I decide to do this in a bomb. If I do decide to do this in the bomb, am I going to get that much energy? No, but when I think about it, most of the reactions, like 99% of the reactions you do are constant pressure. And only about 1% would be in a bomb, which would be constant volume. And so it would be much easier to correct it, the other way. That is, if you do this in a bomb, then we'll have to worry about it. And so basically we're interested in the delta H. Now, and delta H is like this. This is a different notation. Petrucci in the book, he usually doesn't do this per mole. It's just written as minus 566 kilojoules with this missing. The reason this is missing is because this refers to the reaction as written. And so the reaction as written is per 2 moles of CO2 formed. And so this would be minus 566 kilojoules per 2 moles of CO2. But in order to form 2 moles of CO2, you need to react 2 moles of CO. So this would be the same thing, kilojoules for whenever 2 moles of CO completely react. And we have 1 mole of O2, so this would be per mole of O2. And so this is a little arbitrary here. In fact, to clear that up, we usually just write kilojoules for the reaction is written. And the same thing here. In this case, this would be the delta H combustion. This is table sugar, sucrose, C12H2211. This would be kilojoules per mole of sucrose combusted. Well, if you have a mole of sucrose combusted, you'll need 12 moles of O2, 12 moles of CO2 are produced, and 11 moles of H2O are produced. And so this would, in this case, be that. Now, this is interesting because this is H2O gas. Normally, we would have H2O, not gas, but H2O, liquid. And the reason is because most of the reactions we do are at what temperature? Not over 100 degrees C. Most of the reactions that we do in our lab is
Room temperature.
at room temperature. So H2O would not be a gas at room temperature. H2O should be a liquid. So this will be a slightly different energy here. Unless they made a mistake. It's possible they could have made a mistake.
Also, the sugar is gas.
Sugar is a gas, so maybe they didn't make a mistake. But the thing is, have you ever tried to vaporize sugar? When people try to heat up sugar, what tends to happen is it caramelizes, it decomposes rather than vaporizes. And so this equation is very odd to me, that this is a gas. So it makes me think that this is a mistake. This is probably a solid, and that's probably a liquid, and this is probably just a typo. But it's okay because we want to see, you know, what looks reasonable, what doesn't look reasonable, as far as this goes. Well, anyway, the point of this slide is not to understand these reactions. The point of this slide is just a notation. Those are notated. And so, what is the significance of the enthalpy change? So we have delta H. Delta H, you know, I like to refer to that as the usable energy, you know, or the net energy, or, you know, usable energy is, you know, I like to think of it as usable energy because the work, we can't use that. You know, the work is going to be done. You can't avoid it either. You know, because when you're working at constant pressure, the volume changes, the work is going to happen. And so, you know, we know that the total energy, delta U, is equal to Q plus W. Now, the W part is like the tax. We can't avoid that. And so what we're left with after we subtract out the tax is Q, right? Q is the usable energy, and this is what we have here. Delta H is equal to Q. Now, does it have to stay as heat? Because it says delta H represents the heat transferred. Does it have to be heat? No. You know, that's just what we could do is we don't have to convert it entirely into heat. Like if you burn a mole of methane, you could convert it entirely into heat, or you could try to do some work, you know, additional work. Well, what other types of work are there? There's mechanical work, electrical work, etc. And so there are methane oxygen fuel cell vehicles that try to minimize the amount of heat and then convert that into electrical work. And so let's read what this says. Delta H represents the heat transfer under constant pressure conditions. No simple physical or molecular interpretation. Well, let's ignore this. This is not important for us. This is important. Is delta H the heat under constant pressure? Well, that's QP, right? Heat under constant pressure. But is that all there is? No, there's two restrictions. Restriction 1, it has to be under constant pressure. We see that here. What's restriction 2? No, not constant volume.
Constant temperature.
Not constant temperature. Although the temperature is going to be constant, that is constant in the sense that the initial temperature and the final temperature are the same, but the temperature can change in between those two. And so the temperature doesn't have to be maintained as a constant, just whatever temperature you start, that should be the final. Gas, we've been using the gases as ideal gases. I'm going to talk about real gases. I skipped that van der Waals thing. The reason I skipped the van der Waals is, one, I forgot to cover it, and two, because we don't really do anything. We treat all our gases as ideal, right? And so we'll talk about real gases a little later, but everything in this whole book is going to be assuming the gas is ideal, everything. And the only time we worry about a real gas is right at the very beginning of the, or very end of the chapter 6. And so gases are ideals just taken as a given for the entire book.
Is the other restriction work is 0?
Not work is 0, but the other...
Or there's no work done?
No. No. The other restriction deals with work, but it's not that work is 0 or no other work, or work is not done, or
It's
whatever.
'cause volume doesn't, there's no volume change, so take pressure.
No,
instead.
well, in order to maintain constant pressure, you have to allow for volume changes. If you don't allow for volume changes under constant pressure, it's no longer going to stay under constant pressure. You know, the pressure is either going to go down or go up, unless the volume changes to compensate, and we have to make sure the volume changes to compensate. There are two restrictions for delta H, or enthalpy. What are they? One is constant pressure, it's the heat. The heat, you know, we should just say delta H represents the energy transfer. You know? the reason I say energy transferred is because it doesn't have to stay as heat. We could do more work. If we do more work, we're going to get less heat. If we do less work, we're going to get more heat. You know, so we can change that energy. You know, the energy that's lost can be converted into heat and or work. We call it the heat. There's a reason we call it the heat, though, and the reason is because the other restriction on delta H.
Constant volume.
Not constant volume, not friction.
It can only P delta V.
Only P delta V work. That's the reason we call it the heat, because we only allow for one type of work in this. And it's what we call the natural work of a chemical reaction. And you can't avoid that because, you know, you got to allow for the volume to expand or the volume to contract depending on if the system grows or the system shrinks. You have to allow for that. And so the natural work of a chemical reaction is going to be the other component of this, and then the remaining energy we'll just call Q. But that remaining energy, the Q can be, it doesn't have to be Q, it doesn't have to be all heat, it could be converted into more work, just not the natural work of a chemical reaction. And so this is the reason why it's called the heat of the reaction. The heat of the reaction doesn't have to stay as heat. It's just the other term, the Q term versus the W term. And the W term here is a natural work, in other words, P delta V or minus P delta V work. Does that make sense or not? That makes sense. Okay. And so delta H represents the energy transfer, energy